All right. So welcome everyone to the fourth meeting of UQSL. It is my pleasure to introduce Florencia Hunziker from the University of Colorado Boulder, and she's going to be talking about tensor categories arising from the Virasoro algebra.
Great, thank you so much. Thank you very much to the organizers for the invitation. And I'm going to be talking about joint work with Thomas, Cuibo, David, and Jinwei. I love the name of the seminar, by the way. Okay, so we're going to start just recalling some definitions and some simple formulas for the Virasoro algebra, and then we'll get into the Vertex algebra part of things, and then we'll discuss this tensor category structure. So let's just start by defining the Virasoro algebra. The Virasoro algebra is a Lie algebra with infinitely many generators, one for each integer, Ln. And then there's a central element C, and the commutator is given by this. And it's actually a universal central extension of the Witt algebra. The Witt algebra is the Lie algebra of derivations on the Laurent polynomials. And we can think of the derivations of the Laurent polynomials as this space, in which we can grab a basis of this kind. And if we just take the bracket of those things by just taking derivatives and grouping things together, we actually, by grouping things and making derivations act properly, we end up with this relation. So the bracket of L and M is n minus m ln plus m, which is like the first thing that you can see here. So the Virasoro algebra is just an extension with the central element in which we use this scalar. We could use another scalar, but it's just, this is our favorite scalar to extend the Witt algebra. If you don't like that scalar, that's cool. We can talk about it more. You have to choose something to extend it in a way that's consistent with the Lie algebra axioms, and it turns out that you can choose this or any multiple of this, and you'll be fine. And that's all you can choose, actually. Okay, great. So the Virasoro algebra is that Lie algebra, and it has Verma modules, just like other Lie algebras. It has some standard representations that are lowest weight for us. It could be highest weight if you prefer. And the first thing we need to do is get some sort of triangular decomposition if we're going to define induced modules. So we're going to call Vir plus this part of the Virasoro algebra. And we're going to grab a one-dimensional module, and we're going to give it a one-dimensional vector space, and we will give it a Vir plus module structure by making Ln kill this vector if n is greater than 0. We're going to let L0 act diagonally by a scalar h, which is a complex number. And we're going to let the central element also act diagonally by a scalar c. Yeah, so this C and H are two complex numbers that we kind of put right next to this vector that's generating this one-dimensional vector space. And now that we have a Vir plus module structure, we can induce a module over the whole Virasoro algebra, and this is the Verma module. It's a pretty standard construction that we do for all the algebras, or for the algebras that have a triangular decomposition. So in some sense, you can think of the negative part of Vir as acting kind of freely here. And just graphically, this is what the Verma module looks like. It has some lowest weight module, and then I can act on that. It has a lowest weight vector. I can act on that vector with L minus 1. I can act again with L minus 1, or I could just act with L minus 2. And if you look here, I have L minus 1 cubed. I have L minus 2, L minus 1, but I don't have L minus 1, L minus 2. And there's a Poincare-Birkhoff-Bede type of argument that actually tells you that you can rewrite any element with everyone that's showing up in this drawing. So remember that this was the commutator for the Virasoro algebra. And if, for instance, we have this element, L1, L minus 2, 1 is an element that does not show up in this little Christmas tree that I have over here. Right? But actually, using the commutator, I can rewrite it in this way. And now it's written in a good way. Because L1, 1 is 0, this is just 3 times L minus 1, 1. So it corresponds to this element over here. Yeah? And if you have something like this, very similar to this element, except it's in the wrong order, you can rewrite it using the commutator as this. So it is actually true that this little tree here contains all of the elements. Obviously, it's infinite, but this is the list of all of the elements in this Verma module. Great. Note that we have a Z graduation in which we're going to call the n space of the Verma to just be expressions of this form. We're applying L minus things to the lowest weight vector, and we ask that the sum of this indices be n. Yeah, we will need this graduation when we want to talk about vertex algebra modules. That's why we're kind of making this remark. And so this will be the 1 space, this is the 2 space, this is the 3 space. And just like in the algebras, we have, in general, we have an irreducible lowest weight module that's just the quotient of the Burma. Yeah? And it's important, and this happens for other algebras, that J may be trivial. So you could draw a Burma of all the Burmas, and it could be already irreducible. For very specific values of C and H, your Burma will not be irreducible, will have an actual non-trivial submodule that's maximal, and quotiented it out by that maximal submodule will give you the irreducible. This will be important for us because we will distinguish between Burmas that are irreducibles that are equal to Burmas and irreducibles that are not equal to Burmas, but quotients of Burmas. Great. Okay, we're gonna recall what the definition of a vertex algebra is. And the first thing we need is a vector space, a distinguished vector that we call the vacuum, this 0 over here, and a map of vertex algebras. It's a linear map with coefficients in endomorphisms of P. That's nice enough. So when you actually evaluate this map in an element of our vector space, you end up with a series with coefficients in endomorphisms of P. But once you evaluate those endomorphisms in one element, you only end up with finite and many poles here. Yeah? Algebraically, you can write that as A and B is going to be 0 for n large enough. Notice that there's a shift here in the powers of Z, so that positive Z's correspond to poles in this expression. So there are singularities, but they're not so bad. Great, and this vector space satisfies certain actions. The vacuum actions say that you have to send the vacuum to the map that's the identity. What do I mean? There are no coefficients with C to the n with n positive and no coefficients with C to the minus n with n negative. There's only one coefficient with Z to the 0, and that's the identity. Yeah, so the power series with coefficients in endomorphisms has no power of Z, has no Z involved, and it's just the identity. Moreover, when you evaluate the vertex algebra map on this vacuum vector, you end up with something that has no poles, and you can therefore evaluate it in C equals 0, and you recover A. There's a Jacobi identity, just like we have a Jacobi identity for the algebras. It says that if you kind of take the commutator of this map, you end up with the corresponding composition of maps, just like the Jacobi identity in the algebras, except that we have to correct the Jacobi identity so that it makes sense. So you can think, I won't get into details with this, but you can think of these 3 expressions as analytic continuations of the same function in different domains of the complex plane. And that's what those deltas are here for. And equivalently, and this is kind of cool, you can avoid the Jacobi identity and instead ask for a linear map that satisfies this. When you take the bracket of T with the vertex algebra map, it behaves like the derivative. It sends the vacuum vector to 0, and it satisfies the locality action. The locality action says, well, 2 maps, YAZ and YBW, almost commute. They don't really commute. But after you multiply them by a power of Z minus W that's large enough, they commute. Yeah? And these actions in purple here are equivalent to the Jacobi identity. Great, so what's a vertex operator algebra? A vertex operator algebra is just a vertex algebra that's C graded, such that each graded component is finite dimensional, and actually there's some sort of lower boundedness. So Vn is 0 for n sufficiently small. There's another distinguished element that we call omega, usually referred to as the conformal vector, which satisfies that if we expand omega through the map Y in this way, And I'm putting minus n minus 2 on purpose, even though that's not the notation that we originally chose. But it's so that things are a little clearer. If I expand omega with y and I call Ln the endomorphism that shows up right next to the z minus n minus 2, then those Ln's satisfy the relations of the Virasoro algebra. Where C is just some number that we call the rank of this VOA. VOA stands for vertex operator algebra. So basically, a vertex operator algebra is a vertex algebra with a representation of the Virasoro algebra inside and a Z grading. That's nice. And we also asked that the Z grading reflects the way L0 acts on every vector, and that L minus 1 coincides with T, that linear map that we had in the previous slide. Great. Let's do an example, because it's a pretty technical definition. Maybe you are already familiar with it. If not, let me just give you an example of who's a vertex operator algebra. The easiest vertex operator algebra is the Virasoro vertex operator algebra. So Frankel, my advisor, and Zhu proved that actually, if you grab the Verma module of central charge C and conformal weight 0, so H equals 0 and C equals any complex number, well, that's not a vertex algebra. But once you mod out by the submodule generated by L minus 1, 1, you obtain a vertex operator algebra. Yeah? If you think about it, we said L minus 1 has to be T, and T of the vacuum has to be 0. So it's reasonable to mod out by L minus 1, 1. Yeah? It's still hard to show that this is a VOA, but that's what they did for any central charge, and we're going to call this one N sub C. And then let me show you how it's a vertex operator algebra. So we grab the Verma module, which looks like this. And then we kill everyone in the submodule generated by L minus 1. So you can see these crosses here. We kill those guys. They're gone. And once we update, we've killed L minus 1, 1. So they don't show up anymore. The structure is the following. Well, the vacuum is just the lowest weight vector. T is just L minus 1 as a map from V to V. The conformal vector is this first guy that we see over here. And then y, we have to define y. Why am I not defining y on this vector? Well, because the actions already say y of this guy has to be the identity, right? So I don't have to worry about that guy. The first guy I worry about is this one, L minus 2, 1, which I called omega, the conformal vector. So on purpose, I just define it as this power series where I am jamming all of the Ln's from the Virasoro algebra into a power series on purpose. Shift it in the right way, and I'm going to call this power series that I built L of Z. Great, so now that I have L of Z, there's actually a generating theorem for vertex algebras that says you can do this. Grab that field that you had and define y of shiftings of L's as some ordered product of derivatives of that power series. And if you haven't seen ordered products before, ordered product just means reordering things so that they converge. As I mentioned, we have poles here, so we have to be careful when we multiply things that coefficients are actually numbers, yeah, or endomorphisms. That makes sense. So in order to do that, we have to order things in the proper way, and that's what this normal ordering is about. Great, so this is the structure of BOA on MC. And we will also need to define what's a module for a vertex algebra. So one way to think about a module for a vertex algebra is to say, well, it's a module where it's a space in which all of the actions for a vertex algebra that still make sense hold. But let's try to see what that means in a little more detail. A vector space W that's Z grade for us. Well, I say Z and C this in the same way. I'm sorry about that. But for us, it will be Z graded. It could be graded by the complex numbers, but we'll think about it as Z graded. Together with a linear map that now has coefficients in endomorphisms of W. So it eats someone in V, but it speeds up a power series with coefficients endomorphisms of W. And again, it's not so bad. What do I mean by that? Well, when you evaluate it in an element W, you end up with something that has poles, but they're not so bad. There are only finitely many negative powers of Z. It sends the vacuum in V to the identity endomorphism of W. It behaves like derivatives with respect to T or L minus 1. And it satisfies a Jacobi identity. Just like in the algebras, we have YW, 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 and here we have YW and Y of the action of V. And again, we have to correct this Jacobi identity with some deltas for it to hold. And again, because you're a module for a certain vertex operator algebra, you also have a representation of the Virasoro algebra inside you that has the same central charge, the same rank as the vertex algebra. Yeah, so it also needs to carry an action of the Virasoro algebra that's consistent with that action that existed on the VOA. And moreover, we're going to ask that each Wn in this grading is an eigenspace for the action of L0 with eigenvalue n. Great. And actually, we're going to kind of also ask that the dimension of each of the grading components be finite and that there's some lower boundedness. So there are a lot of grading restrictions that we can actually erase to obtain a more general notion, which is that of a generalized module. So if we cross out the last two conditions, we replace Wn being an eigenspace with Wn being a generalized eigenspace, then we have the definition of a generalized V module. So a generalized V module is just a module for a VOA that's relaxed. We don't ask that the graded components be finite dimensional. We don't ask that the module be lower bounded. And we let the graded components be generalized eigenspaces instead of just eigenspaces. Okay. The easiest example of a module for a vertex algebra is the Verma modules. The Verma modules, as you can imagine, are all modules for the VOA M sub C that we defined, that we studied before. So if I graph the Verma module MCH, then that guy is a module for this vertex algebra in the obvious way. What do I mean by that? We're going to define Y sub W to be the map that sends an element like this to this, which is still an endomorphism of W. And we extend it with this generating theorem for VOAs. Great, so we have at least, I mean, I will say the definition of a VOA is a technical definition, so it makes sense. If this is the first time you're seeing it, it makes sense that's a little too much. But what's important about this is that the Virasoro vertex algebras are like the most basic example, and all of the Verma modules are modules for the vertex algebra. Great. There's this very cool result by Zhu that associates an associative algebra to any VOA. So the Zhu algebra of a VOA is defined as a quotient of the vertex algebra by the span generated by elements of this form. And I know it looks very arbitrary, but what's interesting about this algebra is that it's not just an associative algebra with this product, but that there's a one-to-one correspondence between irreducible representations of the associative algebra, which are easy to study because we know associative algebra, and irreducible representations of VOAs, which are hard to study. So that's the importance of this Zhu algebra. And for Virasoro VOAs, one can show actually that the Zhu algebra for our favorite vertex algebra of the day is just a polynomial ring in one variable. And the Zhu module for this Verma module is the polynomial ring in two variables. So in particular, and this is the isomorphism, sorry. It's important that Zhu algebras are compatible with quotients. And note that from this, we know that there are infinitely many representations for the polynomial ring in one variable. Therefore, there will be infinitely many irreducible representations for this vertex algebra. Great, so for every central charge C, I see that someone raised their hand. Theo.
Yeah, so you very carefully did not say that the categories of representations are the same. Did I catch that right?
Yes, that's correct. It's just the counting is what we used, if that makes sense.
Okay, is it true that the categories are equivalent? Is it always, like, when is it ever true?
I think it's not true, and is it ever true? It's possible, but unlikely. That's what I would say.
Okay.
But there's a way to go from an irreducible module to a representation of the associative algebra that's very efficient and clear. But coming back is not so good. Like, you could start with it's not so clear how to come back from a module for the associative algebra to an irreducible for the VOA. But it is true that the number of irreducibles for one is the same as the number of irreducibles for the other one.
Okay, thanks.
Yeah. Great. So important about this is that our Virasoro vertex algebras are in some sense bad because they have infinitely many non-equivalent irreducible representations. This is why in 2020, we're talking about us proving that there's a tensor category in this for these guys. If they had only finitely many irreducible representations, it would be much more manageable. We only recently have a theory that kind of can construct tensor categories in categories that have infinitely many irreducibles for vertex algebras. I'm sure in tensor category theory, there are many of these resources, but in vertex algebras, for modules for vertex algebras, we only recently have this theory developed by Huang, Lepofsky, and Jiang. Okay, so one thing that we will use very heavily is that for the Virasoro algebra, Fagan and Fuchs in the 90s really described everything you can describe about their representations. So what do I mean? They gave all of the Verma modules. They gave a list of which ones live inside which others. They gave a list of which ones are reducible, which ones are irreducible. They described Verma modules and maps between them completely. And they actually proved that the only way two Verma modules can talk to each other is through an embedding. So they gave a list. For instance, if you fix a central charge C, I can give Fagan and Fuchs give a list of all the H conformal weights such that the Verma MCH is reducible, and we're going to call it H sub Z. And for example, for a central charge equal to 1, they showed that the only way the Verma is reducible is when H is m squared over 4. And moreover, in that case, they actually tell you what the singular vector is or what it looks like. It looks like this. So singular vector, I mean the vector that generates the proper submodule that lives inside this Verma that's not irreducible. So they give you like a formula for the singular vector, and they tell you how to build it. We won't focus too much on this, on what this formula is, but they give you, in principle, an abstract formula of how you could obtain the singular vector. And they tell you, well, H sub 1, meaning all the H's that make m1's H reducible are the ones of this form, m squared over 4. Let me just say that again. All the values of H for which m1 comma H is reducible are H equal to m squared over 4. Great. Moreover, they give all the embeddings between them. So for instance, if the central charge is less or equal than 1, then this is what the embeddings look like. There's either only one Verma inside another Verma, and that's it, or there are two Vermas inside another Verma. And then, I mean, it's a little vague in this slide because I don't want to get into details, but they actually give you which HIs show up here. And when C is greater or equal than 25, this is what the picture looks like. So it's just finite diagrams. But again, either this Verma lives inside this Verma or two Vermas live inside a Verma, but that's it. So just to show you what happens for central charge 1, they show you that there are just two possibilities. M1 only has M11 inside, which has M14 inside, etc. But M114 doesn't talk to M11. So these are disjoint chains of embeddings. This means, for instance, that when you want to get the irreducible, you have to grab this Burma and mod it out by this Burma. So the reason why I'm saying this is because our proof of the tensor category uses that we have a lot of knowledge about the Virasoro algebra, singular vectors in there, Burma modules in there. Great. Okay, let's go back to vertex algebras. If the central charge C is of this form, then we are in what it's called the minimal models. The irreducible is not just the Verma divided by or mod out by the submodule generated by L-1, but there are actually, you need two singular vectors to generate the maximal submodule. So in this case, our vertex algebra is not irreducible. You still need to mod out by a submodule in it to get the irreducible. Yeah? But once I mod out by that submodule in it, I get an irreducible, and actually the Zhu algebra changes. It's not the polynomial ring anymore, it's the polynomial ring mod out by something that's non-trivial, and therefore it's finite dimensional. So if the central charge is one of the minimum model central charges, then there are only finitely many irreducible representations that are inequivalent. And Lepofsky and Huang developed a tensor product theory that actually applies in that context. However, if the central charge is not of this kind, then as we discussed before, the irreducible is the same as our vertex algebra. And therefore, the Zhu algebra is this, and there are infinitely many irreducibles. So here's the goal of our work. The goal of our work is to check whether the logarithmic tensor product developed by Huang and Lepofsky and Jiang applies in this context. And as I said, it's a little crazy that we're just showing that there's a tensor product structure in the easiest representations for the easiest vertex algebra in 2020. Okay, I'm going to say a little bit about tensor product for VOAs. We won't get into this. All I'm going to say is that if you grab the tensor product of two modules for a V algebra, it's obviously a module for the V algebra again, right? And we kind of probably all know how this action goes. You just act on the first factor, tensor the identity, plus the identity acting on the second factor. Cool. However, if you try to do this with MC, that doesn't work because the central charge now becomes 2C. Do you agree? Just from this line over here, the rank would become 2C. So there is no hope in just defining the tensor product to be just the tensor product of the modules as vector spaces. That's not going to work. That's not going to stay in our category. So actually, for modules for a vertex algebra, the correct notion, and we could change it to a correct notion, is the PC tensor product that Huang, Lepofsky, and Jiang developed. And it just, you can think of it as the restricted dual to a subspace of the dual to M1, M2, satisfying certain compatibility. So this is based on an idea from Kash and Lustig. They grabbed a subspace of the dual that satisfies certain things and dualized it. And then Huang and Lepofsky did that in a more general setting. We won't get into the details of what the tensor product is. I guess this slide is here just to show you that it's not trivial to construct a tensor category in a category of modules for a vertex algebra. Great. So we want to try to show that there's a tensor category structure for modules of the Virasoro algebra. In principle, if we choose all the modules, that's not going to work. So what we have to do next is choose which category we're going to propose to be that category that has tensor structure. And in order to do that, we need to know what C1 confinite means, because that's one very important notion in the theory of Lepofsky, Huang, and Jiang. So if you have a vertex operator algebra of this form, so it has only non-negative weights, and you define the positive part to be the strictly positive part. For any W module, for any V module, I'm sorry, W, we define the C1 space to be this space. What does this mean? You can take the -1 product of the vertex algebra of anyone that's in the strictly positive part of V acting on anyone in W. We're going to say that W is C1 confinite if the dimension of W mod out by the C1 space of W is finite. Okay, let's see what this means in the case of the Virasoro algebra. In our case, the strictly positive part starts over here, right? This one has weight 0. This one has weight 2, 3, 4. So if we're going to restrict ourselves from the strictly positive part on, we just have to look over here. Great. That's what it says here. If you look at the conformal weight is L minus 2, 1. So actually, it is true that L minus 2 can be obtained as the -1 product of some element in our vertex algebra. However, note that L minus 1 cannot be obtained in this way, because like the lowest weight thing that we have is this guy in weight 2. If we only restrict ourselves to the positive weight members of this vector space. Okay, so when we take the quotient of a Verma by its C1 space, we end up with this. If we look at C1 of a Verma, we're going to obtain anyone that can be written as an L minus 2 times something or L minus 3 times something. We're never going to get L minus 1 times something. Does that make sense? Beautiful. So when we take the quotient of the Verma by its C1 space, we end up with this vector and this vector and this vector. This one is in C1 because it's an L minus 2 something. This one, everyone is in C1 except vectors of this form. So it's an infinite dimensional vector space, and we can see that Verma modules are not C1 confinite. So Verma modules are not going to be useful for a module, our candidate category to have tensor structure. Okay, what if we were to try to fix this by taking, instead of the Verma module, the irreducible quotient of the Verma module?
Sorry, can I ask a question?
Yeah.
So are you saying that you need C1 confinedness in order to have this Huang-Lepowski Jiang tensor product theory?
Yes.
So you're just eliminating. You're kind of eliminating.
Exactly. Yes. Yes. So C1 confinedness is one of the main ingredients of their theory, and that's why I'm introducing it here. And we're kind of seeing what's going on with these modules. That's right. So
okay, great. Thank you.
If we want to restrict ourselves to C1 confinite modules, we have to throw away Vermas. Always. All Verma modules are bad. They're not C1 confinite. If instead of the Vermas, we focus on the irreducible quotients of the Vermas, thanks to Fagin and Fuchs, we know that the singular vectors look something like this. The reason why I'm putting this formula here is because it's important that it's L minus 1 to the sum power times the lowest weight vector plus something that involves either an L minus 2 or an L minus 3 or an L minus 4. In this second expression, not everyone is an L minus 1. Yeah, and this is good news for us. Why? Well, because we're thinking of the irreducible, which is the Verma mod out by some singular vector. And this expression is in C1 of MCH, right? Because we just said some of this, one of these guys is an L minus 2, L minus 3. We're about to take a quotient of MC by its submodule generated by a singular vector. So we're going to get that this L mod out its C1 space is going to be isomorphic to M mod out its C1 space coset in some sense. Yeah, so we're about to kill this thing because we're going to take quotient by the submodule generated. And when we kill that thing, we get that because it's 0, it's also in C1. Which tells us that this power of L minus 1 is in C1, and that's great. Because now when we take L mod its C1 quotient, we end up with finitely many powers of L minus 1 that are not members of C1L. And this tells us that actually irreducible modules which are not Vermas, irreducible modules that are Vermas mod out by something, are C1 confinite. Which is good news for us, because then we have the candidates for our category. Great, so here's what we're gonna do next. Oh, before we go to that, sorry, I should mention that it follows from Fagin and Fuchs that if you grab a lowest weight module, then it's C1 confinite if and only if it's not isomorphic to a Verma module. We just proved that. Beautiful. A C1 confinite lowest weight module MC has finite length. This follows from the work of Fagin and Fuchs. We did not prove that. One can see that by just manipulating singular vector formulas that they gave in their work. And the composition factors of a C1 confinite lowest weight MC module are not Verma irreducibles. It's like, if you are C1 confinite, you better have composition factors that are LCH, not MCH. Yeah, it's like, it's not only that you are not a Verma, no one in your resolution can be a Verma. Great, so.
Sorry, can I?
Yes.
I think this is probably just me not being able to keep up, or I missed something. How big is this set H sub C?
It actually depends on C.
Let's say I'm not in the minimal model case. I sort of understood minimal models, but otherwise.
Yes. So even, let me just say maybe two things. Say C is 1, then yeah. H sub 1 is all of the m squared over 4 with m a natural number or 0. So okay. 0, 1/4. Did that make sense?
Yeah.
So there's infinitely many values, but discrete and nice, it's a discrete and nice set for every central charge. And also, let me just clarify one tiny thing. Maybe if you already know the minimal models, even in our case, because we're not taking the reducible vertex algebra, but the most general vertex algebra, there are also infinitely many representations in that case, if that makes sense.
Oh, okay. Yeah.
Before you mod out by the second singular vector.
I see. So I hadn't realized that too. Okay, thank you.
Yes. So actually, our proof deals with all central charges.
Okay.
I'm sorry, but countably many or not?
Yes. Sorry. So are you asking if there are countably many members of H sub C?
Mm-hmm.
Yes, absolutely.
Okay.
Yes, and it's actually it's not just countably many. There's explicit lists generated by Fagin and Fuchs. So if anyone needs that paper, it's a paper from the 90s, and it's in a book, and it's hard to find on the internet. So like, send me an email, and I will send it to you.
Okay, thank you.
Yeah. Great. Okay, so we're in good shape to kind of try to define our candidate category. We're going to grab the category of finite length. Whoa, that looks terrible. I'm so sorry. Okay. Something strange happened there, that I'll just say what it is. It's the category of finite length MC modules with composition factors that are isomorphic to reducibles, not Vermas. That. And then we're also going to grab this other guy. It's going to be the category of lower bounded C1 confinite generalized MC modules. So we're grabbing two different categories. One has to do with what we've studied. If we think about C1 confinite modules, the other one has to do with what is usually needed to apply Huang's, Lepofsky's, Xiang tensor category. What's good about the first one is that it's closed under taking submodules, direct sums, quotients, and contragradient duals. And what's cool about the second one is that Miyamoto already proved that it's closed under PC tensor product. Yeah? So here's what we did. What we did was prove that these categories coincide. You definitely need the category to be closed under taking submodules, direct sums, quotients, and contragradients to have a tensor category structure. And then Miyamoto already proved that the tensor product works here. It's closed. If you PC product two modules, you obtain another module. So this is what we proved.
So sorry, when you say closed under contragradient, are you telling me that when you're talking about tensor categories, you're including rigidity? Maybe you said this earlier, I missed the beginning.
That's the dream. So our dream always in tensor categories for vertex algebra is to prove rigidity. It's very hard and usually extremely hard, but we actually did prove it for certain central charges. That's why, and that's exactly why we're including that there.
I mean, maybe contragradient dual is something straightforward? You just take duals of every eigenspace or something like that?
Yes, that's right. That's right. Yes, that's right. And there's a way to define a reasonable action of the vertex algebra on the contragradient dual. That's right.
So it's not obviously the tensor dual.
That's right. It's not obviously the tensor dual. That's right.
Does it end up being?
But you show, but Juan Lepofsky-Xiang showed that that ends up being the tensor dual.
Okay.
But you have to show a ton of properties, like for the, for the dual, for rigidity to hold and the dual to exist as a module, you have to show a bunch of properties. But once you check that, then they assure you that that is the tensor dual, if that makes sense. Okay, cool. So let me show you how we prove that these two categories are the same. Okay, the first contention, inclusion, let's go with that. But the other one sounded like Spanglish. The first inclusion, it's more or less easy. So if you grab a finite length generalized module with no Fermat irreducible subcomposition factors, then there's a resolution of this kind in which each quotient is an irreducible that's not a Fermat, but then it's a C1 confinite module, and you can lift C1 confinedness. So then that tells you that everyone in this resolution is C1 confinite, including W, and you're done. Yeah, so that inclusion is actually more or less straightforward. The other inclusion is a little more complicated, and what we did was the following. So the first thing we do is use that we have a lower bounded C1 confinite dude, and we can grab a smallest eigenvector for the action of L0 with a smallest eigenvalue, I'm sorry, for the action of L0 with an eigenvector that's not in C1W. Because W is lower bounded, you end up showing that that W that you chose is a singular vector, meaning it's killed by all of the LNs with n greater or equal than 1. But that means it generates the lowest weight module in this quotient. Beautiful. We just iterate this process. And this lowest weight module in this quotient is lower bounded and C1 confinite again. We just do the same thing in that space, W mod W1, which is the smallest eigenvalue and an eigenvector that's in the space, but not in its C1 subspace. And again, we can see that that guy generates the lowest weight module in this space. That means that I can lift it. There's a W, there's a W2 containing W such that this quotient gives me W2 bar, which was the lowest weight module. And again, I get that W mod W2 is C1 confinite and lower bounded. So we're basically generating a bunch of lowest weight modules inside our W by only assuming that W is C1 confinite and lower bounded. We just continue doing this, and we end up with a sequence of epimorphisms in which and this process ends because we're always choosing an eigenvector in W, but not in its C1 space. But by definition of C1 confiniteness, this space is finite dimensional. So this is definitely going to end in a finite number of steps. Moreover, each of these quotients are lowest weight modules, and the last step occurs when there's no one to choose in a space and not in its C1 space. But actually, you can show pretty straightforwardly that if this happens, then W mod Wn is 0. So it turns out that we actually obtain a bunch of injections of this kind. There was a W here in principle, but we just showed that that guy is 0. So we end up with this sequence of submodules where each subsequent quotient is the lowest weight module. Using the Fagan-Frooks embeddings, we show that these are not just lowest weight modules, but they're finite length C1 confined lowest weight modules. And that is, I'm not going to get into it, but it's an important part. Like, it's not clear yet that this is giving us a resolution of irreducibles that are not Fermas. In principle, there could be someone there that's the lowest weight module, a Fermat, that ruins everything. But actually, one could show using explicit singular vector information that this is not the case, that the lowest weight modules appearing in the sequence must be C1 confinite. So once we have a resolution like this, in which each subsequent quotient is C1 confinite, we can actually extend it to enough people in the sequence so that every simple showing up is an LCHI. Beautiful, and this shows that this categories actually coincide, and this is the proof of our theorem, which says that for any central charge, the category of finite length MC modules, it should say generalized MC modules, because simple composition factors are isomorphic to non-Berma irreducibles, has a braided tensor category structure. And moreover, for generic central charges, this category is rigid. So actually one can show that in this case, the category is semi-simple and simples have duals and then obtain rigidity in that way. Let me just, so some future work would be to try to prove rigidity in all cases, and adapt the proof to apply this logarithmic tensor product theory to other VOA module categories. As I mentioned, we used quite strongly that we had a lot of information on the Virasoro modules. So in principle, our same proof may be useful, but cannot immediately adapt to attack other Vertex modules. And thank you so much.
All right. Thank you very much, Flora.
Thank you. I hope it wasn't too fast, but we can go back if you have some time. Thank you. Thank you.
Thank you so much. So I'm going to go ahead and stop the recording and we'll do some questions